Hello everyone. What you see here is a neural network being trained not using traditional backpropagation, but by using a gradient-free optimization technique. These techniques are also called population-based techniques, as they involve sampling a number of candidate samples in the model parameter space, and then converging these samples towards the global minimum in some way. In this video, I'll explain 3 such techniques and show how we can implement them from scratch in Rust. We'll also implement a basic feed-forward neural network like the one you see here. So let's begin. There are several reasons and/or situations when we might want to use gradient-free approaches to solve an optimization problem. First of all, these methods are pretty easy to implement. Then they perform quite well in parameter spaces that are noisy or discontinuous and contain a lot of local minima. They're also pretty efficient while optimizing simple models, that is, models with parameter spaces having a low number of dimensions. And they're also better suited at tackling problems where calculating the derivative explicitly can be hard. Gradient-free methods don't come without any cons, however. They are usually heavy on the computation side, as the entire parameter space needs to be uniformly sampled, and the number of samples required for convergence rise exponentially as the number of dimensions in the parameter space are increased. The time to convergence in these methods also vary quite a lot, depending on the initial sampling. Though with a larger number of samples, according to the dimension of the model, there are some proven convergence guarantees. Now I'll take you step by step through the entire implementation. First up, we start by defining a feature vector type. This is essentially a point in a continuous parameter space that describes a possible solution to our optimization problem. For a neural network, this would be the flattened list of connection weights. We use the const generic parameter dims to specify the dimensions of our parameter space, which we will be using throughout the implementation. This allows us to use the stack to store all of our feature vectors for the entire population of samples and avoid any heap overhead. The objective function is essentially the function that we aim to minimize. It takes in a feature vector as input and produces a score for it, which is then used by the gradient-free optimizers to navigate the parameter landscape. Some of the gradient-free optimizers can also be modified to deal with categorical data. However, we stick to a continuous real valued parameter space for the purposes of this video. The function that we'll be using to test our optimizers will be the XOR function. It's an extremely simple nonlinear function. The inputs and outputs to the function are discrete and are given as follows. The function outputs 0 when both inputs are the same and 1 otherwise. As you can see, it's not possible to define a linear decision boundary for this function, and hence it's perfectly suitable to demonstrate the power of a simple neural network, which is a universal function approximator. We define our objective function to be the mean squared error of our network output over all input pairs. I won't go into the details of neural network architecture in this video, as there are very many great videos available on this topic on YouTube. All we need to understand is that neural network can be fully represented using the number of layers in each node and the weights of all the connections between each successive pair of layers. Then a feed-forward network performs this matrix multiplication z equals wx plus b to obtain the values at the nodes of an incoming layer from the values at the outgoing layer. W here is the connection weights, x are the inputs at the outgoing layer, and b is a bias term, which is a constant. Coming to our neural network, we have the layer size vector that stores the number of nodes in each of our network layers, which basically represents the architecture of the network. The connections vector consists of a flattened list of all network weights for connections between every pair of successive layers. For our default initialization function, we initialize a network with an input layer size with connection weights of zeros. The layer size input slice is converted to a vector, and the connections are initialized for every pair of successive layers. Notice that for the layer that has the outgoing connections, we consider an extra node. This is necessary to account for the bias term, which outputs a constant value of 1 at all times. Then we have the feedforward function, which is essentially the only function that we need for our neural network since we're using gradient-free techniques and hence do not require an error backpropagation implementation to train our network. Here, we start off with a mutable vector that stores the inputs for a current layer, obviously starting at the input layer. And then, for each pair of successive layers, we add a bias term with an input of 1 to the vector of input values, call the number of nodes in the outgoing layer as n1 and the incoming layer as n2. Then, we define a mutable vector to store the outputs for the incoming layer. And for each node in this layer, we compute the sum of the term wx, as we saw before, by multiplying the value at the input node by the corresponding connection weight pointing to the current output node. Then we push the output to the vector of output values by applying an activation function to the sum. We shall look at the activation function in a moment. Then we set the values vector to the new vector and continue feeding our inputs forward through the network. Finally, we return the list of output values. The activation function that we are using here is the leaky ReLU, or leaky rectified linear unit. As an exercise, you should try out different activation functions like sigmoid, 10H, ReLU, etc. and see which ones perform best. This activation function provides certain benefits for gradient-based methods, like addressing the vanishing gradient problem. It also seems to perform well in our case due to the fact that the activation stays linear for larger values, unlike the sigmoid function, which squashes all large input values to a value close to 0 or 1. In general, a more discriminative function helps the optimizer to discriminate better between different solutions. Then we have some helper functions. The dimensions function essentially returns the number of total dimensions for a model, that is the total number of connections in our network. The from feature vector function takes in a flattened list of connections and populates our network with those weights. We first assert whether the dimensions of our network and the length of the input matches, and then for each pair of successive layers, we map the value n to the total number of connections between those layers. And for each node from index 0 to n, we assign the corresponding connection weight from our flattened list of input weights and increment the flat index. All of the three methods that we're going to be implementing today use the concept of a population. A population is just a term for a collection of sample solutions, which are then independently tuned to arrive at the global minima of the function. Along with our DIMS constant generic parameter that we used earlier, we define a size const generic for the size of our population, again for efficiency reasons. We define a number of samples to represent the potential solution for our problem, an array to store the scores for each sample, an array to represent the sorted order of our solutions to treat better or worse samples differently, a boolean to indicate whether our optimization has converged to a good enough solution or not, and finally another unsigned int to store the number of iterations that we've already made. The update scores function is responsible for updating the scores for each sample using the objective function that we're trying to minimize. The scores array is set by iterating through each sample, mapping the score function to each one of them, collecting the values in a vector, and then converting the vector to an array. A point to note here is that unwrapping in this way all the time isn't advisable in Rust, because your program can unexpectedly crash in case of an error. But for our implementation, since we know that the sizes of our arrays are the same, doing this is fine. It was possible to avoid this issue entirely and just use a for loop instead. However, throughout the implementation, I also would like to show you how simple it is to express something in a functional style in Rust that I wrote the code this way. So most definitely, everything that I'm writing here isn't perfect, nor is it perfectly consistent or optimized. Anyway, moving on, we populate the sorted order array by going through the scores array, mapping the index and score into a tuple, and then sorting the iterator in increasing order of scores, so that the best sample with the lowest score, also known as the global minimum, appears first in the sorted order. The reason to store the sorted order this way is again efficiency, such that all our samples can be modified in place and still be queried in sorted order. Finally, if the first index in the sorted order, or the global minimum, satisfies a given convergence criteria, we can set the converged flag to true. Then we have a set of helper functions defined. The set ith best function takes in a new feature vector and sets the ith best sample to the new value. The get ith best returns the ith best feature vector. The get ith best score function returns the current ith best score, and the global best function returns the global minimum sample. A few more helper functions are used to return the converged flag and the number of iterations, as well as incrementing the iteration counter. Next, we define a population solver trait and specify a single update function that needs to be implemented for this trait. The update function takes in a population, a random number generator, and an objective function that updates the population according to the corresponding algorithm that implements this trait. Traits in Rust are used to define composable behavior for structs and other data entities. We use this trait here as all of our population-based optimizers would use the same function signature. The equivalent way that this would be done in OOP languages is by means of something like an abstract base class, which a derived class will then inherit and implement the required pure virtual functions. With composition using traits, though, we avoid the issues of inheritance in a typical OOP language. The genetic algorithm belongs to the class of evolutionary optimization techniques and replicates how genes are passed down from parents to offspring, with the genes with the best fitness surviving to the next generations. This Wikipedia article is a great resource to understand what genetic algorithms are, their several variants, and their limitations. I'd also recommend the book Algorithms for Optimization to understand optimization techniques in more detail. I've put a link in the description of this video. What we need to understand here is how the core logic of crossover works. Essentially, we have a couple of solutions with a good objective function score or fitness score, which we consider as our parent genes. Then we can construct a child gene by randomly selecting parts from either of the two parent genes. One way of mixing and matching is the one-point crossover scheme, where the selection of the child gene gets switched at one crossover point. Then there can be a 2-point crossover or a k-point crossover, as shown here. In our implementation, we use the uniform crossover scheme that randomly selects a bit from either parent with a 50% probability. We define a unit marker struct, genetic solver, and implement the population solver trait for this struct. This requires us to implement the update function. We start off by updating the scores and sorted scores arrays as they are initialized with default values by the constructor. Then we check whether the algorithm has converged already, in which case we simply return. Then we perform the core logic of the algorithm, which I'll get to in a moment. After the core logic is completed, we increment our iteration counter. The core logic of the algorithm goes like this. We define a retention cutoff index, which is the index until which we retain our best samples without modification. We also use these samples as parents to generate new child samples to replace the other part of the population that lie outside the retention cutoff. For each index that we wish to replace, we pick two parent samples randomly. These feature vectors in a genetic algorithm are similar to parental DNA that are then mixed in the crossover scheme to generate a child DNA. This is done using the crossover function, which I'll get to in a moment. If then the new child sample ends up having a better score than the current ith best sample, we replace the current sample with the new one. The crossover function takes in two parent samples, a mutation probability, and a random number generator. An empty DNA is initialized, and for each dimension, we generate a uniform random number. If this number is less than the mutation probability, we ignore the parent DNA values completely and generate an entirely new random number. This helps in the exploration factor and the optimization and helps the population not getting stuck in some local minima regions. Otherwise, if the random number is greater than the mutation probability, we generate another uniform random number and choose a random bit from either of the parents with a 50% probability. This scheme is called the uniform crossover scheme. These are the constants that we use in our implementation. The mutation probability is set to 0.1 and the retention percentage is set to 0.5. This means that each bit has a 10% chance of mutating and the best 50% of the population are retained. Here you see our implementation of the genetic algorithm in action. On the left is a histogram plot of the resultant mean error from each of our samples in a population, ordered from best to worst. The error from the best sample is plotted on the right, and the corresponding neural network is plotted below. The color coding of the weights are done from red to green, where red maps to -1 and green maps to 1. The blue neurons are the variable value neurons, the leftmost two being the inputs to our XOR function, and the rightmost one being the output. The orange neurons are the bias neurons, which output a constant value of 1. The neural network architecture here is a 2x4x1, which leads to a dimension size of 17 for our optimization parameter space. I'm using 250 samples in my population, but I've had good results on lower sizes as well. As an exercise, I encourage you to try out different architectures and population sizes and observe how the convergence changes. Doing such experiments are essential to understanding how learning and optimization works at a deeper level. Differential evolution, like genetic algorithms, is another technique that belongs to the class of evolutionary algorithms. It involves combining the genes from 3 or more parents to produce an offspring. You'll see how this is done in our implementation in a moment. Just like with the genetic solver, we define a union marker struct, differential evolution solver, and implement the population solver trait for it. The update function is also similar. We update the scores and sorted scores arrays and check for convergence before the core logic. In the core logic, we initialize a new samples array. In our DE implementation, we are not retaining any samples, but try and replace each one of them. We run a loop for all indices, and for each index, we sample 3 unique parent indices using the sample unique index set function. I'll get to the function in a moment. Once we have the 3 parent indices, we assign them to 3 variables A, B, and C, and then for each dimension D, the new sample at the current index is calculated. With a given crossover probability, the value at bit position D for the new sample takes on the value A plus differential weight times B minus C. Otherwise, it keeps the value at the current bit position. This has the effect of moving the current position in dimension D to where sample A lies and is perturbed in the direction of B minus C. If there are large variations in this dimension, more of this range will be explored. Otherwise, the values will remain pretty close to the optimal values found thus far. Then, for each new sample, if the objective function value is better than the current sample is replaced by the new sample. The sample unique index set function works as follows. We only sample parents out of the first few best samples given by the best percentage. We calculate the cutoff index and initialize a hash set. We insert the current index in the hash set and then keep sampling random indices using the cutoff index and inserting them into the hash set. Care should be taken to not run this algorithm with a very low population size so that we don't get stuck in an infinite loop. Once the loop terminates, we are certain to have 4 unique indices in the hash set, including our current index. This is because the hash set only allows unique elements and discards duplicates. We remove the current index from the set and then return the remaining 3 elements as a vector. The constants that we use in our differential evolution solver are as follows. The crossover probability is set to 0.9, the differential weight is set to 0.8, and the best percentage is set to 0.5. Here you see the differential evolution implementation in action. I've kept the size of the population same as with the genetic algorithm implementation to be able to compare the results. Overall, I observed that differential evolution converges quicker on average than the genetic algorithm. This might be because in our differential evolution solver, we are employing crossover on all samples of the population, whereas in our genetic algorithm implementation, we're only doing this for the bottom 50% of our population. I encourage the viewers to tweak the implementations to see how they affect convergence. Again, as with the previous method, doing some experimental tweaking to the parameters or even the core implementation can provide valuable insights into the inner workings of these techniques. Using more than 3 parents in a different combination scheme is also something that can be experimented upon. Particle swarm optimization is the third technique on our list today. It belongs to a class of nature-inspired meta-heuristic algorithms used in optimization. As with the previous 2 techniques, it also works using a population of samples, which are also called particles, and moving them towards optimally good locations in the parameter space with the help of global information gathered by the entire swarm. For the particle swarm optimizer, we need to extend our population struct and add 2 new fields. The PSO velocities array, which consists of the velocities for all our samples or particles, and the PSO local best array, which stores the local best position encountered so far by each particle. Then we define a few extra functions to update these fields. The update PSO velocity function takes in 2 numbers, R1 and R2, and a particle index. Then, for each dimension, we consider the distance to the local best particle from the current position and the distance to the global best particle from the current position. The new velocity is then updated in the following way. The old velocity is multiplied by a constant inertia parameter so that a part of the old momentum is preserved. Then using the 2 numbers R1 and R2 and the 2 constants, the cognitive coefficient and the social coefficient, the 2 distances are scaled and added to the velocity. This has the effect of the velocity being directed towards the particle's local best position as seen so far using its cognitive belief or its belief in itself, and also towards the global best position using the social belief or the belief of the swarm. The update PSO position function then simply updates the current position of each particle using the velocity, keeping the position within the range of our neural network connection weight limits, that is within -1 and 1. The local best positions are also updated if the current particle score is less than the local best score seen so far. Then the update function for the population solver trait follows as before, with the updating of scores and the convergence check. Then we update the local best positions for each particle, as well as the velocity and positions of each particle using 2 random numbers, R1 and R2. Finally, we increment the iteration counter. And these are the constants that are used in the particle swarm optimizer. The social coefficient and cognitive coefficients are both set to 0.5. And the inertia is set to 0.9. Finally, here is the particle swarm optimization implementation in action. It is observed that our PSO implementation converges the fastest out of all of our 3 techniques. This is probably because in PSO, all particles are exploring the space close to optimal solutions, whereas in the other two techniques, we are mostly using the values that are passed down from the previous generation. So the exploration factor is higher in PSO, and in the other two techniques, it is mostly dependent on the mutation probability and the crossover probability. Also, it is important to note that the error in PSO doesn't always monotonically decrease as in the other two techniques, as there is a chance of a particle jumping out of a local minimum and exploring the nearby region somewhat randomly for the first several iterations. The main app, including the plots, etc., is written in Bevy, and I won't go into the details of that in this video, but I also put together this small program that does the same in a headless or non-graphical setup. Essentially, we define the inputs and outputs of our XOR function, the neural network architecture, the dimensions, and population size as constants. Then we define our objective function, that is the mean squared error of our predicted results from the neural network and the actual output over all input pairs. Then we define a solver enum and a const solver that assigns the solver to be used. Here I use the genetic solver. And then in our main function, we initialize our random number generator and our population, and then keep running the update function as defined by our population solver trait for the corresponding solver until the results have converged. Finally, we display the results for each pair of input values. So if I run the program again, that's the output that you'll see. And the predicted output for the case where both the inputs are the same is 0, and these are pretty close to 0. And in the other case, when the output should be 1, they're also pretty close to 1. So that's how everything is put together. So that was it for this video. I hope you found this helpful. Please let me know in the comments about the kind of applications you'd consider using such techniques in. Your suggestions and feedback are greatly appreciated and help me a lot to understand the kind of content that I should be creating on this channel. So please do let me know. Until next time then, thanks for watching.